Okay, I hope everyone can hear me. Let's kick this off. Hello, everyone. Welcome. This is Alan Morges here at CrowdField. And today we're talking pressure transient analysis. We're talking about quantifying uncertainty with Ali Sherif Azzi. It's my pleasure to have Ali with us today. Ali and I go way back. We actually met about 20 or
20.
so years ago back at Imperial College and
Yeah.
then at PP when I was doing my internship in Aberdeen. So it's really good to have reconnected on LinkedIn and have him join us as a guest speaker on this very, very, very fascinating topic.
Mhm.
Quantifying uncertainty in pressure transient analysis using Monte Carlo simulation. Just a bit of background info on Ali. Ali is a lead and senior reservoir engineer with nearly 20 years of international industry experience. He's a specialist in fluid mechanics, numerical analysis, and reservoir modeling. Also a professional Scrum product owner and lecturer in project and risk management. So welcome, Ali. It's again pleasure to have reconnected and have you with us today.
Thank you,
Before
Alan.
handing over to Ali, just a bit of housekeeping for the session. We're gonna have about 40 to 45 minutes for the talk, followed by 10 to 15 minutes Q&A at the end. Please stay muted throughout this session. And if you have questions, just raise your hands with a little hand icon at the bottom of your screen and wait for my cue before unmuting yourselves, or simply type the question in the chat box. This session is being recorded for later distribution and it'll be published on our YouTube channel. So with all of that out of the way, I'm just going to allow Ali to share his screen now.
Yeah.
Just give me 1 sec and off you go, Ali. Take it away, mate.
Thank you, Alan. Thanks a lot for the intro. Okay, so I guess you should see my screen now. Yeah. So I will start with the start. Thank you, Alan, for the presentation. It gives some clear view. And I'm going to start right away with the topic. Quantifying uncertainty analysis in a pressure transient analysis. Why is there a need for that? As you saw, I put on the right a typical plot, log plot, with a pressure plot and a derivative plot, and a probability density function of typical normal curves to give you the gist of what is going to be. The reason for that is that in the past we used to have a rule of thumb kind of probabilities for the Welltest results. So it was typically 0.5 for the skin and typical rule of thumb for the wellbore storage and similar things for permeability, mobility, and so forth. So at the end of the day, they were not bad. They were based on experience from people like Roland Horn and Rame and Greengarten. But at the end of the day, if you want to do a specific analysis for one field or one well, it's not accurate enough, I would say. And if you think about, I take an example in North Africa. Typically, we had this geophysic survey that cost about $60 million for a field, or 90 million. But you try to exploit everything out of it. And it's so sad that we have very good data from Welltest, but we don't extract everything we can from it. So the core idea is to fix that. So I will show the methodology that was developed. It was during my master thesis, and a software was done academically back then at Imperial College. I think it was in 2007. And if you see here, it was presented at EAG in Rome in 2007, 2008, if I recall. And we had, for example, some the thing that happened afterwards. I did my job, as a generalist reservoir engineer for 10 years, and I picked again this work and tried to produce a commercially available version of the software. So maybe I will get out of the presentation for a second, just to show you typically how it looks like. So this is the website for the company that I launched in 2019 that produced this software. And again, it's not a commercial presentation. It really has both sides, the technical and the commercial. And so the main paper was this paper that I published together with Alain Gringarten. If Alan remembers that Professor Gringarten was a high authority in well-test analysis, and we tried to produce really a good summary of everything that we need to treat in the fields of well-test confidence intervals. And then it was published again by Dennis Dene in the JPT some years later. So back to it, it was quoted 24 times, among other people by Lee et al. And it comes after a series of milestones that are summarized in the main page of the site. So basically, I hope it opens. Yeah. It's not an exhaustive list again, but Rame started with first work on the uncertainty in Welltest, Gringarten for like uncertainties, but already in '86, so that was quite early. And Horn did the first dedicated publication on uncertainty in Welltest interpretation in '94. My work used everything that is presented here and more, but it was a lot based on Spivey, who managed to produce the right range of uncertainties, but that was very critical. And Alain Gbo, he was not published in a in an international journal, but his thesis was very useful to give the type of function of probability density function to be used. And based on these two work, I could make something comprehensive for that purpose. So I produced at the end two software, one live software online. We will look at it a bit, and an in-house software that is used more for consultancy if you want something very super specific. Yeah. So the difference, the thing is, when you try to assess uncertainty in Welltest, why it has not been done before is that you have two sets of data to deal with. You have the pressure match, so all the match results, so pressure match, time match, match for the factor for finite or infinite conductivity fracture, similar then distance to a fault, whatever match parameter is used for horizontal wells, for partial penetration, and so forth. And on the other side, you have what I call basic data. Sometimes I call it static data, but it can be confusing if you think about static geomodeling and dynamic reservoir modeling. But what is all this basic data is that your data you don't play around too much. You just input them at the beginning, so it's typically porosity, reservoir thickness, oil viscosity, total compressibility, so a mix of lithology, fluid, PVT, but you don't play around with them. The difference between the in-house and the live software is that in-house you can have user-defined functions, so you can put whatever probability density function you want and whatever range you want based on your best knowledge of the reservoir, which is fair. But for like simplification's sake, in the online software, which is I believe pretty good, you have all these predefined, mostly based on Spivey et al. And Alain Gbo studies, and those are pretty accurate. And it does simplify you the job, still keeping you on track. The interaction between the basic data and the pressure match you don't have to deal with; they are accounted for. But when you use our software, the in-house, we have to make sure that the match parameters and the model selected are the same. So something to be careful about. It's less problematic in the live one because it's already pre-handled. Then we run the Monte Carlo algorithm, which produce on the results all the probability density function, and we can extract the uncertainty range on KH, on skin, on wellbore storage, distance to a fault, or radius of investigation. Now, you can understand that there are plenty of assumptions when we do this, and maybe one benefit of the software is that the assumptions are handled already, so there's a lot of work that is saved for you. However, one that we had to do in the beginning is to assume independency of the variables. Now you can argue, is it correct or not? Well, we can still improve, and we plan on improving. But while I was doing this work on the publication, I thought it would be good to investigate which parameter, especially in this set of basic data, are correlated or not. And this is a plot that shows you, a table that shows you which are independent and which are correlated. It's part of the work. I wanted to, give a head start for future research. And there is more to it, is that we don't only have in the dark part correlations, we have very specific equations that link one variable to the other. And I try to record whatever the literature could tell us is relatively comprehensive for all fields about rock compressibility, flow rate, oil volume factor versus other parameters, and also oil volume factor versus total compressibility and correlations that are used for water compressibility, so that one can carry a fully detailed job. Of course, if your company is interested, for example, it's subcontracting to us for this type of work, we know how to do it, and we can do it very efficiently. So, because it can be a hassle, I understand that. I want to show a typical log-log plot, both for those who are among you very knowledgeable already about well testing and those who are not. And what we observe here is a sort of radial flow, what we call radial flow stabilization of this green curve. And when we get to this stabilization, I try to vulgarize a bit. We reach a stage where we can assess the permeability properly. But this is typically for sandstone, which is a single porosity milieu. It's not a fractured milieu. So that's pretty much the same thing. We have a boundary condition here that we can interpret, and from single porosity, I want to show something about double porosity. So before we go on, there's two coefficients we use in double porosity. Is omega, is the ratio between the fracture storage capacity and the bulk storage capacity. And the lambda is called interporosity flow coefficient. It governs the rate at which fluid can transfer between the matrix, through the fracture, And the reason I show that is mostly for those who don't know already about it, because if you look at such a plot, this omega factor here affects the derivative in different way here. And you can see the difference between a typical normal radial flow stabilization like in the sandstone versus this red double porosity phenomenon. The reason I show that is when we look at the software, some of you will know the factors of matching, but some will not. This is also relative to the fracture, whether it's fractured, damaged, acidized. So I wanted to show that to tell you, for example, in the uncertainty in our field, it gets to a logarithmic stage when we address, for example, CD exponential 2s on this plot. These are the type curves, and when you look at this, the magnitude can change by an order of magnitude. It's from a factor 10 each time, and this is not the case for all the parameters, but for some match parameters, it's something to be aware of and something we handle. That's something slightly different. We are moving to the IT side. When you look at the complexity of calculation in IT and CPU time, we are concerned with complexity of calculation. In our case, we are in complexity of n square, but we have a choice of coding and of language as well, which is different from Python, and it's much faster. So typically, if we run 10,000 trials for probability density function, it runs between 1 and 3 seconds. And if we go to 100,000 trials, it goes to 10 seconds max. But we don't really need to go there, and I will explain later, because we had calculated the error ranges. Yeah. Basically, on this one, if you have only 10,000 trial for the PDF, you will get to 0.35% error range, so which is pretty negligible, and that's a result of the central limit theorem. Yes. Okay, am I on time?
Tracking good, Ali. It's all
Tracking
good.
good, yeah. Okay, 20 minutes. Yeah, I think we can manage. Let me just refill. And I think this is pretty simple plot. I said it's one telling example how to assess or do the appraisal of oil and gas reserves. Yeah. So what I try to explain is very simple but very important, and I hope it will lead in oil companies, mostly operators, but also service companies to different, like, better. They is imagine is the reserves estimate on your field, and you have to decide if you go on with settling a production facility, pipelines, and go for production. The problem with this plot is that you may have a nice, let's say, recovery in the mean, but the probability is very flattened, and the probability to go broke or the probability to go more wealthy is about very similar. And I've been on fields like that in Algeria where we had very nice mean, but the probability density function was so flattened that everything had almost similar or same order of magnitude probability, and it doesn't help to make an economic decision. The benefit of this well-test approach with uncertainties is that you can better assess the productivity, and you can narrow it to the A plot, to the red plot, and eventually say, oh, this project is economical or non-economical. Of course, it can go both ways. So that's very, very useful, I think. Another stage is not so much exploration, is more or appraisal, is more field development. I think I spent 4 to 6 years in field development, which is a very unique kind of environment for those of you who have been there. And the first interest is when the well test compensates for lack of data from core and logs while it's there, and the fact that you can refine this uncertainty is a benefit. The second thing as well that many people from geology don't know, and it creates issues of communication between geologists and reservoir engineers, is that typically your core log has a 40%. Maybe I should not generalize too much, but it has a 40% error. And typically for this permeability, when you do core sample permeability, and when you compare it to well test, in well test is only 15% from the study. So when I talk to geologists, they're very puzzled because they say, how can you have it so narrow? And that comes actually from probability laws, is that if you have an error epsilon on the core, and you average this error along the whole pay zone, then it only gets square root of epsilon, and then proportional to that, and then it goes down to 15%. That's something that we need to better streamline between the two disciplines. The second thing I've been confronted to in field development is drillability. Sometimes the drilling engineer come to you and they want the production index. And if you have a very deviated well or horizontal rather complex well in your 3D model, it's not impossible to calculate, but it's it's a bit tedious. You have to go to the Eclipse files to read some complicated connection factor for each block and try to assess. If you have a proper powerful software, you can have it, but it demands, there is a threshold there. It's not so straightforward. And it's much more complex than on vertical wear. And if you do have the well test information on that, then you can you can better assess it, and it also avoid some simplistic analytical model that use DITS factor shapes and so on. And the third benefit of that is that it helps better assess the pressure for the pressure prognosis. And I remember when we had to provide pressure prognosis for drilling engineers, we prefer to have a wide range than something too narrow that pretends to be very specific. Okay, and now moving to operations. That's a summary, but we mentioned the benefit for exploration. So NPV, reserves, production, productivity, cash flow, naturally. In field development, if you have a better handle on your well testing, you can better fix your permeability, but maybe better use arithmetic average than a harmonic average, for example. And if you have better handle on that, you have better upscaling and then better history matching. Two other things that I mentioned: production index, reliability, pressure prognosis. They're also valid in operations. It's really the same process. So that's why I put these red arrows. And in operation, it's slight difference is useful also in history matching. This plot is maybe it's maybe a showstopper, but what we find from the study as a very generic range is 30% error on distance to a fault, and before the study it was only 50%. It was 50%, and an error on the permeability of 15%. But don't forget, this is a general range that is better than before, but based on many examples. But if you ask us for in-house software and look at a specific field, it might be less than that, or a little more than that. And I wanted to insist on the consequence of the error change on an open reservoir without not being sealed, not closed. It's maybe not so important, the distance to a fault, but the shift from 50% to 30% can really alter considerably the reserves, and it can go down by 50% just between the previous error and the latest error. So it's really important. The seemingly unimportant thing about well-test uncertainty suddenly becomes extremely important. Yes. Everyone is still there? Yeah.
Still here, mate.
Just checking, because so.
Yeah, we are here.
Yes. Okay. Yeah, I wanted the software we have is called MonteCarloFlow, and that's kind of the legacy software keeping the progress down. We are proper engineer of this field. I like CrowdField a lot because it's made by reservoir engineers for reservoir engineers and other subsurface disciplines. And we are many people developing small companies on a small scale, fighting against the inertia of larger ones, for which we have worked before. But the thing is, if you look at Eclipse, for example, it had a very different name in the 90s, and it was developed by a small Norwegian company, then bought over by Schlumberger. So innovation actually comes from a small pot, usually. I don't want to do an overkill, but that's kind of, I try to shadow all the other software. Typical one used for match, and the one we have is handles type curve, handles probability aspect, probability on static data, and match parameters. There is only one or two I come across that do something with match parameter uncertainty, but only ours does the static data. That's, yeah. So this is typical. This is typical result we get from our software. So the mean, the standard deviation, the variance, and P10, P50, P90. I will show you the software live. It will be easier. And if we have time, we can move to some hydrogeology and geothermal. If not, we will stick to the software.
Ali, I think we have some 20 minutes or so. I think it would be very useful, at least from my perspective, to see some actual examples.
Mm-hmm.
I don't know if you have slides on it, or just jump straight to the software to show us.
I think we should
what
jump
does it look like on a PTA itself, an analysis from a probabilistic with a probabilistic workflow and the ranges on the interpretation.
I don't have it on a PTA, but I will show you the software. On a PTA is a bit more. I haven't done it because I don't think it will show up in a very simple way, or it would show up at all. The uncertainty, like a nice plot is maybe nicer on the result. Yeah. I will show you, for example, typically, maybe come back a second. If you look at the website, we have two sides. On the right side is everything with the petroleum terminology, and on the left side is the confined aquifer and confined from a hydrogeology terminology. Given the timing we have today, we'll focus on the right part, on the petroleum. So you have sandstone for oil, sandstone for gas, which you would call single porosity, and carbonates for oil, carbonates for gas, you would call dual porosity. And we also have a module for geothermal and water. So I will start with the sandstone one. Yeah, that's good. So typically you see the input matrix porosity, wellbore radius, oil viscosity, everything called static or basic data like I showed before. And you have PM, TM, pressure match, time match, CD exponential 2S, and distance to a fault by the match parameter, the dimensionless. You have to pick condition of pressure in the reservoir, below bubble point, and above bubble point, and with respect to, for example, 500 psi. And I put dummy values. I put one everywhere just to show you how it works. And the interface might need some, better display. But if we look at KH, we have P90, the mean, P10, the median, P10, the mean, and standard deviation. And we have it for KH, for permeability, for skin, for the mechanical skin, and for distance to a fault. And we have also the plot of the probability density function for the result for KH and for K, and for the mechanical skin and for the wellbore storage. So this is and distance to a fault. So that's how it looks like. If I go to carbonates, you will see a little more match parameters. That's why I spend so much time talking about the how you call it, the lambda factor and omega for double porosity. Yes. So if I just put dummy values here, and I will insist. So you also have conditions of pressure that you have to pick, and you have this match parameter lambda, this match parameter, this typical match that are known by well-test analysts. Yeah. So if I click, as I said, it's relatively quick. It's about 1 to 3 seconds. You have the same display for KH, but for a dual porosity for carbonates and the plots. Yeah. And if I go to the last one, I guess I can show this one, is the geothermal and water. There is a condition for this one because it's not in boiling conditions in the near wellbore area. This one handles water, and you can have a fluid that is in gas form at the surface, but it's the condition for this one is to have it in liquid form in the near wellbore area. But it's a big part of the geothermal wells anyway. And what I should stress, you see, it's a little different from the other ones. You have the bottom hole pressure you need here, the salinity, water viscosity, of course. Yeah. So you have these slight differences. And in the oil industry, we like to deal with our own methodologies. But if you look at the hydrogeology modules, they are very different, and they're based on different equations. So still the same principle. I have to update the plot here, but it's about the same principle. Yeah. I guess we can go for the questions unless there is something specific anyone wants to see.
Ali, on
Yes.
that very screen you're showing, I'm a little bit confused. You're showing the results at the bottom with the probability,
yeah,
P90, median, etc.
Yeah.
And those are numbers being spitted out there.
Yeah.
What I'm not understanding is this is against an actual pressure data deck you loaded, you're matching against. Is these are metrics of what distribution? Is it?
Yeah, it's the metrics, is the how we say, the statistics on the probability density function for the KH, which is the conductivity and the permeability and the mechanical skin and other output like wellbore storage and distance to a fault.
Yeah, but those are the parameters that match your pressure. So you have loaded a pressure check onto this, your actual well test data.
If you look at the previous one, you don't load any specific pressure in the module because you don't need to. Let me check. I don't want to have it to tell you something wrong, so I'll just check quickly. Yeah, that's what I believe. You see here, there is no pressure inputted. Everything is dependent on the match. If you see what I mean,
yeah, but you're matching against that. This is what I'm not getting. So you're matching. Let me go back one step further. So if I were to do a pressure transient analysis the traditional way, deterministic manual approach,
yeah,
I have my data, I load it to the software, I have my history plot, I have my derivative, and then I tweak my KH skin and distances to barriers or limits.
Yeah.
If this is what I understand. Sometimes the data suggests that there could be more than one model that matches data, or
you
combinations
have a point.
of parameters that match the data.
I understand your point, but the question is very different. Handling pressure uncertainty, as you know, like for a Horner plot, is very different from my process, because my process assumes you have figured out your pressure. You understand? You have one fixed pressure. You're sure it's the proper one, and the pressure is. The reason it's not inputted directly in the software is that it goes through the PM to the pressure match. You probably understand that. So that's the reason it's hidden in the pressure match, but it's there. But it's a fixed one, fixed pressure. Now, knowing which pressure is the right one, because you have a certain uncertainty on the pressure, that's a whole other deal that need to be addressed. But it's a different process.
I guess what I'm trying to ask is, I would like to see on a derivative match. Let's focus on derivative shape. You're showing ranges for parameters, and my question is, how do those look on a derivative plot?
The uncertainty, how does it look on a derivative?
Exactly. So is it still matching the data, or this is I'm kind of lost. So you're showing a bunch of statistics or metrics for the distributions. How do those translate into your derivative match?
I think it would be difficult to showcase that on the derivative, because everything else would change at the same time. You would not have a simple envelope. Everything would change, would be affected. Does it make sense?
Yeah, I don't know if anyone else in the audience's specific question. I think, Ali, I am personally confused as to those distributions are for what, to match again, because the way I understand your process is you're still matching against your well test data, pressure being the most important, obviously, time series you load to the process. And traditionally, you go about matching the derivative shape. Let's focus on that. Obviously, you have the history plot, etc., Horner plot, but derivatives is the most intuitive to understand. Each derivative shape suggests a model, and then you match KH, skin, and limits.
I understand.
Now, this is a probabilistic approach, and you end up with ranges for your parameters.
I understand what you mean. I think what you try to mean is, if you move within the range, is it still matching the plot?
Yes.
I think
I would like to visually see that.
That's a very good question. It's the first time I was asked, but I think that needs to be taken out of the meeting. It requires more time to answer properly. It's more complex than it seems. Yeah.
But even more fundamentally, what is it that this is doing then? Because I'm confused. Those ranges are ranges for what?
I can partially answer the question, because you see the match remains the same, because the PM and TM remains the same. But everything that is embedded in it moves and is allowed to move within the probability density function. That's why this method works. But But I gather your question, but it really needs more time than just answering so swiftly.
But if it's not on the derivative, again, on a fundamental level, the ranges that you're presenting are ranges for what? Because
for
again,
the final result of the matching of the Welltest, it's the
what is the matching?
conductivity.
What is the match? What are you matching against? That's kind of what I'm kind
If
of.
I can answer you, is the final result, or the PDF is on KH, K, skin, mechanical
Yeah.
skin. There are reasons for that, why it's skin and not the mechanical and not the total one. A distance to a fault, and
Yeah.
so forth. Yeah. Yeah.
Okay. Yeah, I think we may need to take this offline. Is there anybody
Sure.
else who has a question for Ali in the audience? We still have a few. We have plenty of time, unless you want to go to some screenshots on the software. Or so the software you presented is that is what it presents. It's just a ASCII text formatted.
Yeah, I'm planning to improve the CSS. Believe it or not, there was already work done on it before, but I need to make it more, pleasant. Beside that, yeah, there will be work on the correlations more. I want to present, but that will be a matter of months or years of work to show one with correlated and dependent parameters, at least for those who are that are. And yeah, that's the way forward. But in between, maybe no one has questions, so don't be shy. Please feel free to shoot.
Yeah. Meanwhile, sorry, but I think I want to keep pressing on this issue because I think it's very fundamental to understand, and I think it's just we're lost in translation here. If we are talking about, just to put this as an example, right? If we talk about assisted history matching in a reservoir modeling exercise, you come with your production data, pressure and rates, and a deterministic approach lends itself to one solution, and assisted history matching lends itself to ranges of your parameters, all of which still match to a reasonable degree your data. I would have thought here's a similar thing, but what is the error function here? What you're matching against? This is kind of the piece that I'm missing. I would have thought it was your pressure data, your derivative, you're matching against that, and your ranges are those that satisfy that.
Yeah.
But this is the piece that I'm missing here. Your ranges are ranges for what? That give you what result around what?
Yeah, okay. The ranges are ranges of what I call the basic data, which are the porosity, all volume factor, wellbore radius, and so forth. And the other one, they are produced by the typical software we have in the industry. That most of them, they have they're able to output a range on their match. They give you a sort of matrix with the correlation between them, and also the standard deviation on each of them. And we use that, we input it in our software to get the final results. So we compile both this standard deviation from the typical kappa pi Welltest software or interpret on one side, the match side, and on the other side we have those from the Spivey study, Alangbo study on the other side for non-dimensionless parameters, but actually this other input from the reservoir and the lithology and the fluid, and we compile all of those. Yeah.
Okay, guys in the audience, no one has any questions?
Hello, I'm trying to raise my hand, but I can't. Can you hear me?
Yes.
We can hear you. Go ahead, Joshua.
Yeah, I guess I also have I have missed some stage, like Alan. Like I'm trying to understand at what stage do we need to get these ranges of the parameters, and what do we use it for? Because if I understood, probably you just mentioned a little bit that you do this analysis at the end when you have already matched the model, and the parameters that you get, since they are already questionable, you need to get a range, right? So, but I may be wrong, but you can clarify. I guess there was a little bit disconnection.
Yeah. I think
and where do we end? Yeah.
I think I will partially answer that showing the in-house piece. I think that's the easiest. I saw your question on the chat. So for what I call the basic data, I also come the static data. You have this whole set of IDs found by SPIVE is about the probability density function type. We have many reasons to believe we need to use a uniform probability density function for the PVT factors, and this different type, normal and triangular, for the geometry and porosity inputs. We also have, consideration about corrected by the logs or non-corrected by the logs, and typical standard deviations. That's work from both Spivey and Alangbo and others. Yes. As you see here, for the match parameters, we use a normal PDF. That's also one of the conclusion. But all these inputs, see, I put no assumption here because they come from the typical, legacy software of well testing. And not, I wouldn't say all of them produce this output, but at least 2 or 3 of major ones do it. I think I know Interpret from formerly Paradigm, now Emerson does it, and I think Kappa does it. So you can really load that and find it quite easily in your initial software. And our software is not a competition to this legacy software. It's a complementary tool. It's you use this output from these tools and you put it in ours. And if I try to run, for example, if I try to run it, you will understand maybe a bit more. You see, you have this basic data here, so you can select in the in-house. As you see, it's user defined, so you can maybe shift from this assumption if you wish. If you find something that is very specific to your field, and the GNG guys tells you this is the way it is, and you can pick, for example, triangular. You can select. You can take your low, your mean, your high. Yeah, and yeah, it's a bit. There's a difference between the in-house and the online, because the online we have handling of errors. And for example, if you pick for reservoir thickness normal, you have standard deviation and mean. So yeah. On the other hand, and that's why I said you have to be careful when you have your uncertainty on the match parameters. You have to make sure the set of match parameters is same as your model. So you have model for the early time, wellbore storage and skin, vertical partial penetration, and so forth. You can click OK. You can select your probability density function for each of them. Usually this one is normal. And then you can choose homogeneous or double porosity. If I put double porosity, you have the typical factors you have to pick. If you have homogeneous, there's not much to do. And you have late time as well. So if I take channel and wedge, for example, you have the dimension to one boundary, dimension to the other boundary. Single fault and leaky fault, you have the distance to a fault, and then you generate all the probability density function for all these inputs. Then you run the Monte Carlo simulation. We will produce the PDF for the output, and then you just display it. Yeah. So to show you how it looks like in an Excel spreadsheet. I wasn't supposed. You see, you have the PDF of a distance to a fault, and you have. Yeah, give me a sec. For example, something we are told in theory that the omega match. That's hang on. That's very important. That's something we told that the omega from the derivative is more accurate than the omega from the pressure match, and we actually prove that by generating it numerically, and you can really see it now. You can actually see it. It's not like fuzzy. Yeah, and we have a display with the probability, the P90, P10 for all of this. But I think, yes.
Let me rephrase this and see if I get this wrong. Trying to understand the workflow here. Mm-hmm. So you come into your software with a match already on the table. So you have a pressure match and time match in the dimensionless space.
Mhm.
That's your number one. That's your starting point here in this process, and then you basically end up with ranges of all the key input parameters that still match against those
Mhm.
time and pressure matches.
Yeah.
So that's your starting point. So you would have needed to conduct your match before coming into here to this
Yes.
workflow.
Yes. Correct.
And that is done in a separate package. It's not done within
No.
within the software package itself, right?
Indeed. Yes. It's done previously.
Okay.
Yeah.
So you do your pressure transient analysis elsewhere, and you bring into here in the dimensionless time and
Yeah.
pressure matches, and then you go about running your probabilistic workflow, and you end up with ranges for all the key parameters, and the metrics are the ones that are reported there. Is that correct?
That's absolutely correct. Yeah.
Okay. The attached question then is, when you generate this distribution you have on the screen right now off of the ranges for each parameter, so you have your ranges, you run your Monte Carlo, you end up with a distribution. Where is the match embedded in this process? Because running a Monte Carlo of ranges of parameters, this is not against a data set you're matching against. This is just running Monte Carlo on ranges of parameters. That's it. So where is the match embedded in that process?
The match is embedded in the equation. That is, if your PM is correct and your TM is correct, for example, then as they are fixed, the rest can move freely. The equation is still respected. But again, your question, there are some details that we still need to check offline because, for example, it depends on how much change there is compared to the match. If you see what I mean. If it's not too much of a significant change, it's acceptable. But if it becomes too important, then there is a problem. But I must admit that it's interesting because it's the first time I'm confronted to this question in a long time. Yeah.
So it's in the ranges themselves that still need to honor the match with a certain tolerance or error margin.
Yeah. I guess it's a good way to put it as well. Yeah.
Okay. I guess from my end, it was good to clarify that the match itself is done prior to getting into this workflow.
Yeah.
And you bring into here that pressure time matches in the dimensionless space, which is your key input here. That's it.
Yeah. Something I can mention though, because this is interesting and I need to look at it more, but the pressure, making sure you have the right pressure, that you have reached the full stabilization, is a different thinking, and is a whole other process to reach your proper match, as you probably have learned about it, and that also needs maybe to be reinforced in the industry because
Okay, I think somebody was asking a question. Let me go to the chats. Nikolai, if I get this correctly, we're trying to alternate parameters. Can you read the chat, Ali? So if you go to the chat window, that's Nikolai question.
I get this correctly. We're trying to alternate the parameter to still comply with the TM match allowance we have for the mismatch. Yeah, as dimension cure. How this? Okay. Yeah. No, I haven't made this calculation, but I will keep that. I'll look at that. That's a fair question. That's a fair question.
Yeah, that's kind of a similar
to your point. Yeah.
Again, and in history matching, you're defining a net function with a certain tolerance. Here it would be the same.
But I still feel that this is a fair question. But if you have messed up, for example, your initial pressure match already, that's kind of pointless. So I really think that this match of the initial pressure needs to be done properly before coming to our software. That's something I would stress is maybe more important.
Yeah, no, but even granting that, let's say you do have let's say you did a perfect match, and here you still need you are defining ranges that still give you that match, but within a certain tolerance or an error margin, which is a user defined error margin. So you say, give me all the combinations and ranges that still match within a 3% error or whatever error. So that is embedded in those ranges. So I guess that is what the question was aiming at. What tolerance?
I would not call it 3%. I would say you have a higher tolerance, but that needs to be calculated. We cannot just, have the intuition for that.
Okay, well, we're about out of time. Thank you very much, Ali, for that engaging preso.
Thanks
Keen
again,
to go
Alan.
and have a bit of a play. Good to reconnect once again. Thank you, everyone, for joining.
Yeah, and
And
thanks for all
again,
the people attending again.
I will be sharing the recording and send that email with those additional notes and links for everyone to have a play with the software. Have a great weekend, everyone, and I'll see you on the next one. Cheers. Thanks, Ali.
Cheers. See you. Nada.